Hey everyone, welcome to another session of Amazon ML Summer School. I am Rudra Singh. I work as an applied scientist at Amazon with the international machine learning team. My work is on buyer abuse prevention. So I deal with sequential data and user activity patterns on a daily basis. A lot of what we'll try to cover today, like RNNs, LSTM, sequence models, these are the things that I actually use in production. So let's get started with it. I'll try I'll quickly share my screen first. Now, in the previous parts of this module, you covered MLPs, backpropagation, activation functions, gradient descent, and CNNs. You already know neural networks. You already know how neural network learn and how CNNs handle spatial data like images. In this part, we'll explore how neural networks handle sequential data, things like text, speech, and time series. We'll learn RNNs, LSTMs, GRUs, bidirectional models, sequence to sequence models, and then we'll build one in PyTorch. So let's get started. Here is the plan for today. First, we'll to vanilla RNNs and backpropagation through time. Then we'll move to LSTMs and GRUs. These are the gating mechanisms. After that, bidirectional RNNs, then sequence to sequence models. Then we'll cover PyTorch essentials that includes tensors, autograd, NN module, and data loader. And finally, we'll end by actually building a model in PyTorch. So let's begin. Let's start with vanilla RNNs and understand how they learn from sequence. So first of all, what is a sequence? It is any data where the order matters. Think about when you search on Amazon red running shoes, and that would make total sense. But shoes running red would make no sense at all. The order is what gives it meaning. Same with the customer reviews. Each word builds on what comes before it. And you can take Alexa for an example too. It processes thousands of audio frames every second, and each frame only makes sense because of what came before it. So the key point is this, that each element's meaning depends on what came before. In red running shoes, the word shoes tells you that the running is a type of shoe, not the action. This is the exactly this is exactly what RNNs are designed to handle. Now the question is, why can't we just use a normal neural network for this, like a regular MLP? There are three major problems with it. First is the input sequence can be of variable length, like high is of 2 characters, but a customer complaint could be of 200 words. And as we know that MLP needs a fixed input size, so you'd have to pad everything or cut it short. Padding adds noise to the data and truncating would lose information. So both of them would be a bad solution for this problem. Second, there is no sense of order. Not bad actually means something positive, but bad not doesn't even make sense. If you use bag of words, an MLP sees the same words in both cases and it cannot tell the difference. And even with the positional inputs, what it learns about not at position 3 does not help when not appears at position 50, which in ideal case you'd want a network to learn. So it cannot generalize on all the input sequences that it is seeing. And the third and the last problem is that there is no parameter sharing, and MLP needs separate weights for position 1, position 2, position 3, and so on. So for long sequences, this is wasteful and cannot generalize to unseen lengths. So the idea for RNN is that if we can have some weights that can look at the entire sequence and can be applied at every position, then it will solve all the above mentioned problems. But the main problem is that how can we actually do this? How can one network look at the entire sequence and can be applied at every position? Here's an animation showing how an RNN actually works. So you are seeing a network which transformed into 5 different networks. These are the 5 different cells, and each one is the exact same network. Same weights, same parameters, just applied repeatedly. That's the parameter sharing we have been talking about. One network handles any length of sequence that comes in as an input. The blue dot entering from below are the inputs. In this case, the characters H, E, L, L, O are entering one by one in the network at each time step. The green arrows between the cells are the hidden state H being passed forward. That's the memory the RNN holds. After the first cell processes H, it has a memory of seeing H. That memory flows into the second cell. The second cell sees E and combines it with the memory of H. Now it has HE. The third cell adds L. Memory now holds HEL, and so on. The, the yellow dots coming out the top are predictions. At each position, the model tries to predict the next character. After H, it should predict E. After HE, it should predict L. After HEL, it should predict L again. So this solves all the three MLP problems from the last slide. For the variable length, you can just add in more cells. For order awareness, the hidden states accumulates information in order. And because of the same weights everywhere, parameter sharing is also achieved. Everything that we have learned so far about RNNs have been on spot, but even though they are not used in production today. And here's the biggest reason behind it. Everything we have covered so far works great for shorter sentences, but let's watch what happens when you train RNNs on long ones. Do you see that orange dot? That's the gradient, the learning signal. It started bright and big at the rightmost cell and it traveled backward through the network because during training, that's how weight update works. Gradients flow from the loss backward through time. That's backpropagation through time. In short, we call it as BPTT. I'll rerun the animation. This time, watch what happens to it. At each cell, it gets a little smaller, a little weaker. By the time it reaches the leftmost cell, it's nearly invisible. And that's not just a visual effect, that's literally what's happening to the numbers. Think of it like a whisper game. You start with a clear message, each person passes it along and slightly garbles it. After 100 people, the message is gone, and that's what's exactly happening here. In the RNN, every backward step multiplies the gradient by a factor involving WHH and the tan H derivative. The factor is typically less than 1. So if you multiply something by a number less than 1 over and over and over 100 times, it would eventually collapse to 0. Here's the number 0.9 to the power 100, which is effectively 0, and hence the gradient would be dead. What does this mean in practice? It means that the model cannot learn the relationships between things that are far apart in sequence, as we have seen here, that if the sequence is of 100 length, then the gradient would be 0. And if a customer bought something 100 steps ago and that matters now, the gradient that would teach the model this connection has already vanished and it's now slow learning. The learning signal is mathematically gone, and this is why vanilla RNNs on fail on longer sequences, and this is exactly what LSTM was built to fix. Here's what actually happening under the hood. The gradient flowing from step T all the way back to step K is a product of terms 1 per time step. Each term is a WHS transpose times the tan H derivative at that time step. So you are multiplying these together across every single step in between. The key is the largest eigen value of WHS, what's called the spectral radius. If that's less than 1, every multiplication shrinks the gradient. Chain enough of these together and you would get somewhere close to 0. If it's greater than 1, the gradient would explode and it will be almost infinite. So this one number, spectral radius of WHH, determines whether your RNN can learn long range patterns at all or not. So for example, if it is very less than 1, then it would start vanishing. If it is if it is greater than 1, then it would start exploding, and you would need it to be around 1, which is very hard to guarantee in practice. And this is why in most practical scenarios, RNN fail. So to deal with this, people actually tried 3 different ways. First was gradient clipping. You can cap the gradient norm at some max value like 5. If the gradient gets too big, you scale it down. It fixes explosion, but does nothing for vanishing. So it is kind of half a solution, which in itself is not sufficient enough. Second is truncated BPTT. Instead of sending gradients all the way back through the full sequence, what you would want to do is you can only go back to k steps, let's say 20 or 35 in our case of 100 total steps. It would be faster to train, but now you are artificially cutting off any learning signal beyond k steps. Let's say if you put that number to be 20 or 35 in our 100 step scenario, and now you are still blind to long range patterns just by design instead by an accident. So this also is not a good solution. The third and the real fix is the LSTM. The insight is, what if gradient didn't have to travel through that multiplicative chain at all, because that multiplicative chain is what is either exploding the gradient or is vanishing it. So what if we don't have to um, pass the gradient through that multiplicative chain, and what if there was a shortcut, a highway kind of thing, where the signal flows straight through without getting multiplied down at every step? And that's exactly what LSTMs build. They build a gradient highway, and that's what we are going to learn next. So let's start with LSTMs and GRUs now. In this section, we'll try to first understand what LSTMs are, how are they built, what problems are they solving, and then we'll move on to GRUs. So let's start with LSTM first. So here's a real world example. A customer bought a Kindle 6 months ago, and now they search for the word case on our Amazon site. So the real problem is, should you recommend a Kindle case or a phone case? The answer entirely depends on something that happened hundreds of steps back in their history. So a vanilla RNNs gradient already has decayed to zero long before it reaches that 6 month old purchase. So it literally cannot learn this connection, not even slowly, not even imperfectly, but not at all. The learning signal for the vanilla RNN is mathematically gone. So we need an architecture where memory can persist for hundreds of steps without decaying. That's exactly what LSTM was designed to do. Okay, so let's see how does an LSTM's architecture actually looks like. If you'll see the diagram, you'll see that there's lot going on. So let me walk through it. Let me walk you through it carefully, because once this clicks, the rest of LSTM becomes very obvious. The first thing to notice here is the orange dashed line running across the very top. That is the cell state, the long-term memory, and it flows from left to right almost untouched. This is the highway that we have been talking about. In a vanilla RNN, the only way information moved forward was through a hidden state, which got multiplied and squashed at every single step. And that's exactly why gradients died. So the cell state solves this by giving information a path that can flow through without being destroyed. Now, below the cell state, the previous hidden state ht-1 comes in from the left, and the current input xt comes from the bottom. These two get concatenated and fed into all three gates simultaneously. So every gate sees both where we have been and what we are seeing right now. Let's go through the gates from left to right. On the far left is the forget gate, the red sigma. It takes the concatenated input and outputs a number between 0 and -1 for each dimension of the cell state. Then that number multiplies the cell state at the red X on the orange line. This is this is kind of a filter. An output of 1 means we should keep everything, and output of 0 means we should erase it completely. This is where the network decides that old memory what old memories are of no use now, and that is why we call it as a forget get. In the middle, you'll see there are two things working together. The red sigma, labeled as the input gate, it decides how much new information to write, and the green tanh labeled as the cache should it decides what the new information should be. These two multiplied together and the result gets added to the cell state at the green plus sign. Notice that it's an addition, not a multiplication. So that's the key architectural choice that makes LSTM work. On the right side, the cell state passes down through a green tanh to get squashed into the range -1 to 1, and the output gate output gate sigma decides what fraction of that to actually expose as the hidden state HT. So even if the cell state is holding a lot of information, the output gate controls what gets revealed at that particular time step. Was the colored dot as the animation plays? The orange dot travels along the cell state, it shrinks a little at the forget gate and gets a boost at the top. Then the green dot rises from the input side, it merges into the cell state, and the blue dot appears at the output and becomes HT, flowing down to the next layer. Think of the cell state as a conveyor belt running through the whole network. Information sits on it and travels forward untouched unless one of the gates actively decides to change it. And because of the main path through the and because the main path through the cell state involves addition rather than repeated matrix multiplication, gradient can flow all the way through hundreds of time steps without shrinking to zero. That's the core insight behind LSTM, and that is how they are a far more superior network than RNNs that we had. Now, as you can see, these are the three gates that control the LSTM. Each gate is a sigmoid that outputs a number between 0 and 1, and the number acts like a dial controlling how much information is allowed to pass through at that moment. The forget gate decides what to erase and how much to erase. If a customer moved to a new city, would you want to forget the old address or would you want to keep it? In an ideal scenario, you would want to forget the old address so it doesn't interfere with future recommendation, and this is decided using the forget gate. The input gate decides what new information to write in. If you just learned the customer's birthday, now is the right time to store that. The output gate decides what to actually reveal at this time step. You might know the customer's birthday, but if they're currently searching for shoes, that birthday information isn't relevant right now. So the output gate keeps it hidden. And this is how these three gates actually work in synchronous manner in order to keep the LSTM architecture like. Now let's make this concrete with some actual numbers. Let's say the cell state currently holds 0.8 and minus 0.2, and we have currently a new input as France. And the cell state, you can think of it as the model having remembered Italy from some earlier context in the sequence. The forget gate fires with values 0.1 and 0.9. The first dimension, the country slot, gets multiplied by 0.1. So it drops from 0.8 down to 0.08, erasing 90% of Italy. The second dimension gets multiplied by 0.9. So it mostly stays the same. After forgetting, we have 0.08 and minus 0.18. Now the input gate kicks in. The input gate says write strongly into dimension 0 with a value of 0.95, and the candidate says the new value should be 0.9. Multiply those together and you get 0.855. That's France being written into the country slot. Final step, we would add the two together. 0.8 plus 0.855 gives us 0.08 plus 0.855 gives us 0.935. France is in, Italy is gone, and the gates did exactly what they were supposed to do. And this is how the mathematics behind the gate actually works in synchronous manner. Okay, so let's move on to our next slide, which is LSTM equations. Quick thing to keep in mind before we look at the equations is that sigma always outputs value between 0 and 1, and tan h always outputs value between minus 1 and plus 1. You can think of tan h as what content, the actual values you want to store or read. The first equation, the forget gate, ft equals sigma applied to the previous hidden state and the current input stacked together times a weight matrix plus bias. The sigma squashes the result to something between 0 and 1, and that value decides what fraction of old memory survives. The input gate and the candidate, it looks structurally identical, same formula, just different weight matrices. The network learns entirely on its own, and what each gate should pay attention to based purely on the training signal. Now comes the most important equation. CT equals FT times C previous plus IT times C tilde. In plain English, you would say that take what you decided to keep from old memory and add what you decided to write as new. The crucial thing is that it is addition, not multiplication. And that one difference is why LSTM solves the vanishing gradient problem. Um, because gradient flow through addition without shrinking at each step, unlike what was happening in multiplication because of chain multiplication rule. The output gate and final hidden state follows the same pattern, and the great thing is that in PyTorch you don't have to implement any of this yourself. We'll see that once we write the code and once we do the hands-on, we have to only call nn.lstm and all four gates are computed internally in just one shot. We have seen the equation of all the gates. Let's see why LSTM fixes the vanishing gradients problem. As you might remember, vanilla RNN gradient after 100 steps was around 0.9 to the power 100, which is equal to 0.000265, which is effectively zero, which means the signal is dead. For LSTM cell state gradient after 100 steps is to be 0.9 to the power 100, which equals 0.366, still alive and strong enough to learn from. So you'll ask me that what is the difference and why is it zero point 0.9 to the power 100? Why was RNN zero point 0.9 to the power 100 and why is LSTM 0.99 to the power 100? So along the cell state path, there's no matrix multiplication and no tanh derivative, both of which were responsible for shrinking the gradients in vanilla RNN. Instead, the gradient just flows through the forget gate values. If those values average around 0.99, the signal survives all the way back through 100 steps, and we don't have any vanishing gradient or exploding gradient problem in LSTMs. That was all about LSTM. We'll touch on more things later on in the slide. After LSTM came out, researchers asked a simple question: do we really need these three separate gates? Because that's really a lot of parameters to actually train on. Can we get the same benefit with something very simpler? The answer is gated recurrent unit. In short, GRUs. It merges the forget gate and input gate into a single update gate. The idea is that whatever fraction you forget, you replace with exactly that much new information. So the two new decisions are tied together rather than being independent. The reset gate controls how much of the hidden information influences the new candidate value. When the reset gate is near zero, the model ignores the past and computes a fresh candidate from just the current input, which is useful when the context has shifted dramatically, like the start of a completely new topic. The update gate Z works like a mixing knob. When Z is near 1, the model keeps the old hidden state almost entirely. When Z is near 0, it replaces it with the new candidate. So it's a smooth interpolation between old memory and the new information that we have. The equation ht equals 1 minus z times the new candidate plus z times h previous. So z near 1 preserves old state, z near 0 adopts the new candidate fully. Unlike LSTM, where forget and input gates can act independently, in GRUs, what you erase always equals what you replace. And that is the core principle behind gated recurrent units. And in PyTorch, the API is identical to LSTM. Same input, same output, just swap nn.lstm for nn.gru. Now we have seen how RNNs, LSTM, and GRU works. The main question is when to use what. So it is advised to use LSTM when memory really matters, like long documents, long time series, anything where dependencies stretch for back. Because all three gates are independent, LSTM has the most flexibility to learn complex patterns, which makes it the safe default for most sequence problems. We can use GRU when you need speed or you have limited data. It trains about 25% faster than LSTM because it has fewer parameters, and on many benchmark it performs comparably. If you are doing real-time inference on a phone or an edge device where every millisecond counts, GRU is a strong choice. For a new project today, transformers often win and are worth considering first, but LSTM and GRU still dominate in specific scenarios, like time series forecasting, streaming applications where you can't batch your inputs, and edge deployment where model size is constrained. At Amazon, we still use LSTM based models in production for exactly these kind of use cases. Let's do a quick check of what we have learned so far. So if the forget gate output exactly 1 everywhere and the input gate outputs 0 everywhere, what happens to the cell state? The first option is cell state resets to 0, or the cell state copies the input, or the cell state stays frozen and remains unchanged forever. And the fourth option is cell state oscillates. I'll give you 10 seconds to think about it and answer it in the chat. We can then discuss the answer of it. So the answer is C, as Ct equals Ct minus 1 plus 0 times Ct dash, which is equal to Ct minus 1. So the cell state never changes at all, and it's perfect memory in the sense that nothing gets lost, but it's completely useless because no new information can get written in either. Up until now, what was happening was we needed only the past context wherein, and we were using that past context in order to predict the future token or the future character. So for example, in a single directional RNN that we had seen earlier, what we were having was we were having a character by character prediction, and we were trying to predict the future characters. Now let's say you need something where both past and future context is needed. This is where bidirectional RNNs comes into picture. They help you when you need both past and future context. So you'd ask me that what is the problem with a single directional RNN and why do we actually need a bidirectional RNN? I'd like to give you a concrete example. And let's say someone searches for Apple laptop charger on Amazon. Your job is actually to classify what Apple means in this query. Is it the fruit or is it the electronics brand? If you are reading left to right and you are sitting at the word Apple, you have nothing to the right yet and you have zero context. You genuinely cannot tell that what does the word actually means. Is it the actual brand? It is the electronics brand, or is it the fruit? But you can guess based on frequency. Apple the brand probably gets more searches than Apple the fruit on Amazon, but this is not understanding, this is just a prior. The model is not reading the sentence, it is just gambling, and gambling is not something you would like to have in a production search system which is serving millions of queries a day. But the laptop charger that comes right after resolves the ambiguity completely, and we can see that the context you needed was sitting to the right the whole time, and a forward only RNN is completely blind to it because it cannot look ahead. This is not a rare edge case either. Natural language is full of words whose meaning only becomes clear from what follows. Think about bank in river bank account versus river bank erosion. Think about left, she left the room versus turn left at the corner. Think about I saw the man with the telescope. Did you use the telescope to see him, or does he have a telescope? You need both sides to resolve it, and a model reading only left to right is structurally unable to do this. So for any task where you need to label or classify each position in a sequence, named entity recognition, part of speech tagging, query understanding, slot filling, a forward only RNN is always going to be half blind, and you need context from both directions to do the job properly. So here is the solution. Watch the animation carefully. You can see two rows of cells, um, and where the top row has green dots flowing from left to right, that is the forward RNN reading Apple, then laptop, then charger in order. By the time it reaches charger, it has seen everything that came before it in the sequence. The bottom row has purple dots flowing right to left. This is the backward RNN. It reads charger first, then laptop, then Apple. So by the time it processes Apple, it has already seen everything that comes after it. Idea is elegant in its simplicity. Run two completely separate RNNs on the same sequence, one forward and one backward. They have their own independent weight matrices and they never talk to each other during computation. As you can see in the as you can see in the animation that is there. They just process the same input from opposite ends. Both are trained together end to end with a single loss. So they learn complementary things. The forward one learns patterns that depends on left context, and the backward one learn patterns that depends on the right context of the token that we are seeing in. At each position, we take the forward hidden state and the backward hidden state and concatenate them into a single combined vector. If your vector size is 128, the forward gives you 128 numbers and the backward gives you another 128 numbers. So you end up with 256 number at every position. This is why the output dimension doubles when you go bidirectional. It is not a complication. It is just the natural consequence of having two RNNs instead of one. Now look at this. Now look at what this gives you at the apple position. The forward hidden state says, I started the sentence, nothing informative came before, but the backward hidden state has already processed laptop charger and has encoded the fact that this is an electronics context. Together, the 256 dimensional combined vector has full context from both sides, and a classifier sitting on top of it has everything it needs to label Apple correctly every time. And with this, you might think that why don't we use bidirectional RNNs every time if it has the capacity to read from both the front and the back, then why can't we use it every time? So there is one hard limitation which you need to know. You cannot use a bidirectional RNN for any task where you are generating output one step at a time, like text generation, auto completion, streaming speech recognition, anything. The reason is fundamental that the backward RNN needs to read the future to produce its hidden states. But in generative tasks, the future does not exist yet because you are the one creating it word by word. So as we saw in the example hello, while we were generating H, while we first generated E, we never knew that what would come after it. And let's say after H, we generated I, then we might have ended up having only an exclamation mark after that. In a similar manner, think about autocomplete on your phone. You type how do I re, and the model needs to suggest return or reset right now. It cannot run a backward RNN over what you typed because there is nothing to the right. You have not typed it yet. Same with the Alexa generating a spoken response in a real time. It is producing audio one frame at a time. It simply cannot look ahead at what it is about to say. Bidirectional RNN is fundamentally incompatible with any task that requires generating output before the full input is known. But whenever you already have the complete input in hand before making any prediction, bidirectional RNN is exactly the right tool. Sentiment analysis, you have the full review, so read it in both directions and get maximum context before deciding positive or negative. In named entity recognition, you have the complete sentence, so label each word with full left and right context. In machine learning, in machine translation encoder, you have the entire sequence, entire sentence upfront, so you can encode it bidirectionally before the decoder starts generating. And this is actually how BERT works. It is a bidirectional encoder trained on the full sequence, which is exactly why it became so powerful on understanding tasks. Every time you use a search engine or a recommendation system that understands your query properly, this is very likely a bidirectional model somewhere in that stack. The only thing you have to remember is that the output dimension doubles. So any linear layer that comes after needs to take 2 times hidden size as its input, not just the hidden size. So notice something I slipped in on the last slide. I mentioned machine translation encoder as one of the good use case for bidirectional RNN. The encoder reads the full source sentence bidirectionally, gets full context, great, but I never said anything about what happens after that. How you actually go from understanding the input to generating the output. This is a completely separate problem, and it is what we are covering now. Bidirectional RNN solved one thing, reading a sequence with the full context from both directions, but it still gives you one output per input position. Translate a 10-word sentence, you would get a 10 output vectors. That is fine if you are labeling each word, but what if you would need to produce a sentence in French that has a completely different number of words? What if you need to summarize a paragraph into a single sentence? Bidirectional RNN cannot do that. You need a different architecture entirely. That architecture is sequence to sequence, and it is the bridge between everything we have covered about reading sequences and the actual ability to generate new sentence of any length. Watch the animation carefully. It tells you the whole story. Okay, let me explain what just happened. You saw two group of cells, one on the left, the green cells, that is the encoder. On the right, the blue cells, that is the decoder, and in the middle, that pulsating orange circle, that is the context vector. Let me explain why we need all three of them. The problem that sequence to sequence solves is this. Every model we have covered so far produces one output per input step. Feed in 5 words, you get 5 outputs. But most real tasks do not work that way. When you translate I agree to French, you get "Je suis d'accord." 2 words in, 3 words out. When you ask Alexa a question, your question might be a 10 word, 10 your question might be of 10 words, but the answer could be of 2 or it could be of 20. When you summarize a 500-word article, the summary might be 50 words. The input and output lengths are completely independent, and a standard RNN simply cannot handle that mismatch. So the solution is to split the job into two completely separate phases. The first phase is the encoder. It is a standard RNN, could be an LSTM, could be a GRU that reads through the entire input one token at a time without producing any output. It is purely reading and building up its hidden state. Every word it reads, the hidden state updates to incorporate that new information. By the time it has finished reading the full input, its hidden state contains a compressed representation of everything it saw. The final hidden state is the context vector, one vector supposed to capture the meaning of the entire input sequence. The second phase is the decoder. It starts with the context vector loaded as its initial hidden state. So it begins with the encoder's full understanding of the input. Then it generates output one token at a time. It produces the first word, feeds the word back in as the next input, produces the second word, feeds that back in, and keeps going until it generates a special stop token. This auto-regressive loop where each output becomes the next input is what lets the decoder generate sequences of any length. This is the architecture that powered Google Translate before 2017. It was behind every early chatbots, document summarization, code generation, question answering, any task where the length of what goes in has nothing to do with the length of what comes out. This was the core architecture that was there. But here is the problem, and it is a serious one. See that orange circle in the middle? That is one vector, and it may be of 512 numbers, and it has to carry the entire meaning of the input sentence across from the encoder to the decoder. For something short like I agree, that works fine. But imagine a 50-word paragraph. You are asking 512 floating point numbers to hold all the vocabulary, all the grammar, all the relationship between words, and in the right way for the decoder to reconstruct it faithfully on the other side. It is like trying to describe a detailed painting through a keyhole. No matter how carefully you try, something always gets lost in the compression. And that is not theoretical. Researchers measured it. Translation quality was solid for sentences under 20 words and then dropped sharply as sentences got longer. The context vector simply could not hold enough information. The bottleneck was real and it was limiting everything. This is exactly what motivated the attention mechanism, which is you'll cover in later sessions. The key insight is instead of forcing the encoder to compress everything into one vector upfront, what if the decoder could look back at all the encoder's hidden states, every intermediate representation, not just the last one, at each generation step? That way, it can directly attend to whichever part of the input is most relevant to whatever word it is currently generating. Translating the word accord, look back at the encoder state from where it was reading agree. You will see exactly how this works in the upcoming sessions, and it is the idea that eventually led to transformer and everything that followed. Now let us move to PyTorch. This is where we go from theory to code. Let me explain you the 4 building blocks of PyTorch. First, tensors. A tensor is a PyTorch fundamental data structure. Think of it as a NumPy array. It can be a scalar, a vector, a matrix, or any n-dimensional array. But there are two crucial differences. First, tensors can live on GPU and run operations there in parallel, which makes training fast. Second, every operation you do on a tensor gets recorded in a computation graph. PyTorch tracks how each tensor was created from other tensors. Second, autograd. When you call loss.backward, PyTorch walks backward through that computation graph and automatically computes the gradient of the loss with respect to every single parameter. You never have to derive or implement a gradient yourself. For an LSTM with forget gates, input gates, cell states, that is an enormous amount of calculus. PyTorch just handles it for you. This is also where backpropagation through time happens. Loss.backward unrolls the RNN across all time steps and sends gradient backward through each one. So tensors hold your data and AutoGrad computes your gradients. These two together mean you can build any computation and PyTorch will figure out how to train it. Third, we have NN.module. Every model you build in PyTorch inherits from NN.module. What this gives you is parameter tracking. PyTorch automatically keeps a list of all the learnable weights in your model. It also lets you switch between training mode and eval mode, moving everything to GPU with one call and save and load weights. Fourth and the last one is the data loader. Instead of feeding your data one example at a time, data loader groups your dataset into mini batches and shuffles them between epochs. Mini batch training is more stable than single examples and faster than using the full dataset. You tell it the batch size and it handles the rest. We'll be seeing their implementation in our hands-on demo that we have at the last. All of the 4 pieces that we have talked about comes together in this 5-step loop. Every PyTorch project uses these exact steps. Step 1, zero the gradients. You call optimizer.zeroGrad before every batch. If you do not clear them, gradients from the previous batch get added to the current batch gradient and your updates become meaningless. Step 2, forward pass. Feed the batch through the model. During this step, PyTorch is building the computation graph, recording every operation so it knows how to differentiate later. Step 3, compute loss. Compare predictions against true labels. Cross entropy measures how surprised the model was by the correct answer. Step 4, backward pass. Loss.backward walks back through the entire graph and computes the gradient of loss with respect to every parameter. Every learnable number in the model gets a gradient. Step 5, optimizer step. Adam looks at every parameter's gradient and decides how much to update it. After this, all weights have moved slightly in the direction that should reduce the loss. These 5 steps work for MLP, RNN, CNN, any architecture. The model changes, the loop does not. Now let us build and train a model. I'm going to switch to a Jupyter notebook and walk you through it step by step. Here is what we are building: a multi-layer perceptron classifier, an MLP. It takes in some input features and outputs a prediction of which class that input belongs to. This is one of the most common things you will ever do in deep learning, and it is the perfect way to see all 4 PyTorch building blocks working together in one place. So let's move on to the code directly. First, we import everything we need. Moving on to the next cell. Now we create the dataset. We have 3 classes, 4 input features, and 300 samples per class, 900 in total. Each class is a cluster of points in 4-dimensional space centered at a different location. We then split into 700 training samples and 200 test samples. Notice we have not wrapped anything into a dataset yet. That happens in the next cell when we set up the data loader. Moving on to the next cell. This is the most important cell, and let me go through it line by line. At first, we have class simple classifier and is which is our model, and our model is a Python class that inherits from nn.module. Inheriting from nn.module is what makes PyTorch treat this as a model. Without this inheritance, PyTorch has no way to know that your class is a neural network. It is just a Python object with no special meaning. Then we have this def init line. The constructor takes three arguments instead of hard coding the sizes. This makes the class reusable. You can instantiate a different size network just by passing different numbers. Notice that the constructor is where we define the layers, not the computation. We are just declaring the pieces here. Now we have this self.layer 1 equals nn.layer input dimension comma hidden dimension. This is the first fully connected layer with input dimension equals 4 and hidden dimension equals 32. This creates a weight matrix of shape 4 by 32, that is 128 numbers, plus a bias vector of shape 32. Every one of those 160 numbers is a learnable parameter that gradient descent will update. In the next layer, we have our ReLU layer. Notice that this is defined as a layer in init, not called as a function later. We store it as a part of the model. This is standard PyTorch pattern. Define the ReLU once as a layer and call it in forward. Then we have this self.layer2 equal to nn.linear. This is the output layer. It maps the 32 hidden units down to three output scores, one per class. The class with the highest score is the model's prediction. Then we have the forward function. This is where we define the actual computation. PyTorch calls this method automatically when you write model X. The forward pass is of three lines. Pass X through layer 1, apply ReLU, pass through layer 2. That is it. And we then instantiate with simple classifier input dimension equals 4, hidden dimension equals 32, and num classes equal 3, and print the summary. Moving on to the next cell, now we need three things to set up before training. First, the data loader. We wrap the training tensors in a tensor dataset. That is what pairs up each input X with its label Y, so the data loader can pull them together as a matched pair. Then we pass that to data loader with a batch size of 32 and shuffle equals true. Batch size of 32 means every training step the model sees 32 examples at once, computes a single average gradient across those 32, and does not wait update. Second, the optimizer. We use Adam with a learning rate of 0.01. At third, we have the loss function, cross entropy loss. It is the standard choice for classification. The expected initial loss is natural log of 3, which is about 1.10. That is because a randomly initialized model assigns roughly equal probability to all three classes. Now, let us move to the training loop that we have and let us run it. Since while it is running, let me walk you through the loop line by line. For epoch in range 20, an epoch is full pass through the entire training dataset. We run 20 epochs, meaning the model will see every training example 20 times total. Each time it sees the data in a different randomized order because of the shuffling. For batch X, batch Y in train loader, the data loader splits the 700 training examples into batch of 32 with 700 examples and batch size 32. That gives us 22 batches per epoch. Each iteration of this inner loop is one gradient update step. So we do 22 updates per epoch, not just one. Then we have this optimizer.zeroGrad, which clears the gradient from the previous step. This must be the first line in every training step every single time. And if you forget it, gradients from the last batch accumulate on top of the gradients on top of the current batch's gradients, and your updates become completely meaningless. This is the number one bug beginners hit. So you'll have to put it first every time, and there is no exception in it. Then we have this logit equals to model of batch X. This runs the forward pass. Batch X flows through layer 1, then ReLU, then layer 2. The output is called logits, which are raw unnormalized scores, one per class for each of the 32 examples in the batch. PyTorch is silently building the computational graph in the background as this runs. Then we have this logits equals criterion logits patch of y. Cross entropy loss internally applies softmax to the logits, then computes how wrong the model was for each example. The result is a single number, the average loss across the 32 examples in this batch. Then we have this loss dot backward. This is where backpropagation happens. PyTorch walks backwards through the computation graph and computes the gradient of the loss with respect to every single learnable parameter in the model. After this line, every weight in layer 1 and layer 2 and every bias has a dot grad attribute filled in with a number telling us which direction to move in to reduce the loss. Then we have this optimizer dot step. Adam reads all those grad values and updates every parameter. After this line, the model is slightly better than it was one step ago. Then the inner loop continues to the next batch. Now look at the training output. Epoch 1, the loss is 0.311. Accuracy is 91.4%. Already one single pass through the data and the model is already getting 9 out of 10 examples right. This is because the three clusters in our data set are quite well separated. The model finds the pattern very quickly. Epoch 5 loss drops to 0.005. The model converged almost completely after just 5 epochs, and then the loss is just settling down towards 0. Now we check whether the model actually learned something general or just memorized the training data. We have this model.eval, which switches the model to evaluation mode. This turns off dropout if you have it and tells PyTorch not to track gradients. It is a single line, but it is very critical. If you forget it, two things can go wrong. Dropout keeps randomly dropping activation, so your prediction are different every run. And PyTorch keeps building computation graph for every forward pass, which wastes the memory that we have. Then we have with torch.nograd, this context manager tells PyTorch explicitly not to build any computational graph inside the block. Inside the block, we pass the full test set through the model in one shot. We call test logits.argmax dimension equal to 1. Argmax picks the class index with the highest score for each example, giving us the predicted class. Then we compare those prediction against the true labels and compute the fraction that match. Test accuracy is also 100%, so it is perfect. Now let us look at exactly where the 259 parameters live, because understanding this helps you make good architectural decisions and debug issues with model capacity. The output lists every parameter in the model. Layer 1 dot weight has shape 32 by 4. Notice the shape is output by input, and that gives 128 parameters. Layer 1 dot bias has shape 32, one bias per output unit, so 32 more, and that is 160 parameters total for the first layer. Layer 2.weight has shape 3 by 32, giving us 96 parameters. Layer 2.bias has shape 3, one per class, that is 99 parameters for the output layer. So in grand total, we have 128 plus 32 plus 96 plus 3 equals 259 parameters. And that matches the model summary we saw when we first defined the network. Now coming back to the slide, there are few common issues that we need to cater. First is loss not decreasing, usually means learning rate is wrong, data is not shuffled, or labels are mismatched with the inputs. Second, loss goes to NAN. It might be a exploding gradient problem, or you can add gradient clipping or reduce learning rate. Third is train accuracy is high, but test accuracy is low. That is overfitting. You can add dropouts and reduce model size or get more data. Okay, let me bring everything together before we go to questions. We started with vanilla RNNs. The core idea is simple and elegant. One set of weights shared across every time step and a hidden state that gets updated at each step and carries information forward. That is what lets a single small network process a sequence of any length. But the moment you try to train it on a long sequence, you run into vanishing gradient problem. That is exactly the problem that LSTMs and GRUs were designed to solve. The key insight in LSTM is the cell state, a separate highway that runs straight through the network with the only additive updates. Addition does not kill gradients the way multiplication does. The forget gate, input gate, and output gate are all learnable controllers that decide what to keep, what to add, and what to expose. The gradient can flow backward through the cell state for hundreds of time steps without vanishing. GRUs does something similar with fewer parameters, just an update gate and a reset gate, and in practice performs comparably to LSTM on most tasks. Then we looked at two architectural extensions. Bidirectional RNNs runs two separate passes, one left to right and one right to left, and concatenate the hidden state at every position. That gives you full context at every word, which is exactly what you need for tasks like sentiment analysis or named entity recognition. We saw sequence to sequence, which took a different direction. It solves the problem of mismatched input and output lengths by splitting the work into encoder and a decoder. The encoder reads the full input and compresses it into a context vector. The decoder starts from that context and generates the output one token at a time, auto-regressively. And finally, we have the PyTorch, the four building blocks that are tensors, autograd, NN dot module, and data loader. Every model you will ever build in PyTorch uses all four of them. The training loop has exactly 5 steps: zero gradients, forward pass, compute loss, backward pass, and optimizer step. And that loop works for MLP, CNN, RNN, LSTM, transformer, any architecture that we have. We built a simple classifier from scratch, trained it on three class problems, and watched it go from 91% accuracy after one epoch to 100% by epoch 5. The loop we wrote for that classifier is the same loop you would write for a production LSTM. So that is from my slide. You came in today knowing roughly what a neural network is. You are leaving knowing how RNN processes sequence and why they break on long ones, how LSTM and GRU solve that with gates and a cell state highway, how bidirectional models give you full context at every position, how sequence to sequence handles variable input and output lengths, how to build and train a neural network in PyTorch from scratch. That is a lot of ground to cover in one session, and I hope it clicked. The notebook is yours to run. Everything in it is self-contained. Change the hidden size and a third layer. Try a different learning rate. The best way to make this stick is to break it and fix it yourself. So that's it from my end. Thank you for joining in for the session. And if you have any questions, you can ask them in the chat now. Thank you.